So yeah, my name is Daria Mesbah, and I'm an R&D engineer in a company called FEniCSx Labs. I do my best so that we can have lunch on time. But before, I'd like to thank you for giving me this opportunity as a newcomer in the FEniCS adventure to present you femOHL, or femOHL according to the audience, which is our FEniCS-based solution allowing to assess the structural integrity of overhead power lines. So if we take a step back and have a look at the process of electricity production until, let's say, consumption. If on one end of the cycle you've got the power generation, so production of electricity through nuclear plants or renewable assets, and on the other hand you've got the substation with the transformation of high voltage until low voltage current. In the middle we've got something called the power transmission. So basically, it's all the infrastructures allowing to transport electricity using different kind of components such as pylons, cables, and other accessories. And so in the context of climate change, these infrastructures may be subjected to different kind of extreme events. And what's funny is that in a 3-day conference, we faced 3 out of the 4 events that are listed here. So we had there are snowfall, rainfall leading to flooding, massive heat waves, and storms. And so the project I'm talking about is in collaboration with RTE, with the logotype in below, which is the French transmission system operator of these infrastructures. And so RTE has defined a roadmap, a 10-year roadmap, allowing to focusing on the grid renewal and the adaptation to this climate change context. And this involves more than 24 billion euros investment over the next 15 years, including the renewal of more than 20,000 kilometers of lines and more than 85,000 pylons to be replaced. So there's a key challenge behind this, which is the one of prioritization of these interventions on the aging, climate exposed, but also strategically critical assets. And that's where FEniCS Labs come up. So we defined a partnership with RTE called PALAS for physics of overhead lines, intending to develop numerical tools. So we've got a family of tools called OWLs. And this family allows the management of overhead line assets, bridging multiple scales of analysis. So some tools focuses on the infra components, but also other on the scale of the network, going from upstream research and development until the operational decision support needs. And all of this in another challenge of the open innovation approach. So here is a map of the different tools we included in this OWLs family. But today we'll focus on femOHL, which is the FEM-based software allowing to assess the overhead lines integrity. So femOHL appears to be a solution allowing to create a digital twin of these infrastructures. Different components have been modeled in this software. Pylons made of Timoshenko beams elements. Here, I'd like to thank all the people creating tutorials and the people that are active on the forums. So yeah, beam elements with an elastoplastic behavior. The geometries are extracted from industrial files, giving access to the section of the different element of the pylons. And aging effects has also been included through corrosion. Conductors are, so the cables, are truss-like elements with an elastic behavior. And since this software is to be used by engineers, we used engineered parameters from the industry to characterize the cables, such as the mechanical tension at 15 degrees, the temperature, and other material properties. Insulators, well, these are not the main topic here, but some accessories have been included in the software. And the last point here is the foundation. So here we include them as beam elements, but what is important here is that the behavior used to describe the foundation behavior is derived from high-fidelity 3D FEM simulation as part of another project between Muse Labs and the RTE, enabling, and also POM, I think, that is included. And this simulation allows to predict the pull-out of this foundation in case of storms. And so regarding the key capabilities of the software, so the software translates some environmental conditions into mechanical loading. So here we included the gravity, the corrosion, but also wind using different kind of profiles, constant or logarithmic in altitude, and constant in time or variable. We included snow and frost as additional weight, and temperature effect intending to reproduce the thermal strain. The software has been deployed using the Docker image of FEniCS, and two types of solvers exist, so nonlinear static analysis, but also dynamic. And so here is the first simulation that you'll see on femOHL. So that's a sinusoidal wind applied to the cables. And here the magnitude is quite low. That's the reason why there's no effect on the pylon. But in case of storms, this could have an impact, and until to reach the collapse of the pylons. And that's the case study we're gonna see right now until the end of the presentation. So in case of extreme wind loading, such as the one we faced in France in 1999, so the cyclone had a German name, I don't know why. And this pylon collapse may cause some local damage to the nearby assets, but also it can initiate cascading failure along the overhead line, leading to a major service interruption. And so that's not something RTE wants. And so we developed femOHL in order to answer to three objectives. The first one would be to identify the critical zone of the pylons, to define an engineering criterion to define when there will be a collapse. And the third objective is related to the wind condition leading to collapse. So we run dynamic simulation first on isolated pylons subjected to wind gusts until to reach this collapse. And the first output here is that the critical deformation zone is quite consistent with what is observed in the nature. So this is our experimental data. And the second point that I want to raise here is that the simulation didn't go until the collapse, so until the contact with the ground here. We faced divergence issue. And so in order to overcome this, because this is an industrial project and the project must go on, we defined a point, so at divergence, and at this point, we developed a rigid body motion in order to see the collapse. But I would be glad if you have any comments on this so that we can solve this divergence issue. So as a conclusion, I presented you femOHL, so the FEM software based on FEniCS, allowing to run static and dynamic simulation on the overhead line infrastructures. I presented a kind of a first industrial case study intending to prioritize these adaptation actions. And so femOHL appears to be kind of a bridge between the open source scientific computing with a quite complex problem that can be solved and this industrial decision support workflows. And so the next step would be to move from an isolated pylon to a span, so at least two pylons and the cable, but also the line level, so to have multiple pylons, multiple cables. We would like to strengthen the reliability of some industrial tools, such as the reinforced anti-cascade pylons that are reinforced pylons intending to stop the cascade failure. And so let's improve together this post-collapse FEM modeling. And the last point would be to integrate femOHL into an industrial decision support workflow, combining both this deterministic mechanical point of view with some probabilistic point of view coming from the meteorological condition in some area of France, for instance. And so, using this, I'd like to thank you all for the attention.
Thank you, the speaker. Thanks for this interesting presentation. Do you have any questions, please?
So I'm just backing off here a little bit and saying, the first question would be, were the pylons designed badly? That would be the first thing to test. But then what you really want to know is where has some rust occurred that has weakened a pylon? So how do you find that out? Well, one thing to do, well, first of all, you simulate to know where, what would it look like if, here it was rusted or here it was rusted, right? So that you do. And then you say, what do satellites tell us? So satellites can actually see movement everywhere, right? You need something global to assess the entire network.
Actually, there's another project including satellite images, SAR, so radar, intending to check the motion of the pylons. So yeah, that would be an interesting way to initiate the solver with the actual position of the pylon. So yeah.
Great.
Yeah. Thank you very much for the talk. I know that every 10 pylons or so, there's like an anchor pylon to avoid the domino effect. Like, is it something you take into account?
Exactly. Yeah. So in the scenes we try to reproduce, let's say the biggest scene would be the scene between two anchor pylons. So between these two anchor pylons, you've got suspension pylons. So yeah, these are the pylons that could collapse.
Thanks a lot. Next question.
Regarding a problem with the divergence, it reminds me of elastic multibody systems. Do you know it?
No, but I would be glad to be here.
Where you allow for large deformations, like rigid body deformations, but you also allow for small strain deformations within your finite elements, so that it has at least the same background. So that might something you want to look into.
So that's
elastic multibody system.
Okay.
EMBS.
Thank you.
Thanks a lot again for the speaker.